Okay, so this is going to be our video for Tuesday for our notes, which are going to be pretty fast and succinct. But we've talked a lot about integrals as area under curves, and one of the things we're going to lead that into is, well, what if I want to find a specific area of something? So for example, here, what we have and what we're actually going to be focusing on is if we have two curves, which is just another way to say two lines or two graphs, what is the area between those curves? And I actually want to first off change this. Well, I'll talk about it instead of just changing it. Okay, so we want to find the area between the curves from 0 to 4. Well, let's look where are the curves in between. Where do they touch, really, is what I care about. And I'm noticing they touch here and here. And I'm going to have to sync it manually because it doesn't want to load, but we're touching here and here. Those aren't pretty points. So I'm not going to worry about the actual computation, but now let's think about how we can find that area. Well, if I'm looking at the area of, let's call this green one F, well, that area under the curve is going to be everything here. So all this area right here in between where I drew those green lines. And then if we look at the area for G, which I'll call the blue function G, well, that area is just underneath the blue curve. Hopefully this shows up nicely. I'm not sure if it will or not, but we'll find out. So that's this area right here. But we only want this top area in between F and G. We want the area between the curves. So let's shade that one as this orange color. That's the area we want. So we have essentially another geometry problem of part plus part equals whole, but we have the whole thing and we want to take away a part. Well, what is our whole thing? And I'll go ahead and write this. We're doing the integral from 2 to 4 because that's where our function intersects. And our whole thing, well, our whole thing was the top function, was our bigger function, f. So that's our whole. And we want to take away our piece. Well, our piece was the smaller function, g. To take away, that's the same as subtracting. So we're going to do our whole function minus our small function. And let me actually label that as well. This is our bigger function. And then blue was our smaller function. Okay. And that's the big idea for today, is we're doing the integral from some interval from our bigger to our bigger minus our smaller. The tricky part is really figuring out where these points exactly are. But let's go to our next example and we'll see how we can do that. So our total area of the regions between the curves, they give us the two curves. They don't tell us where they touch, and they don't tell us which one's bigger. So we have to do a little bit more math here. We don't have a graph to give us that nice picture. But, well, if we want to figure out where they touch, we want to figure out where they're equal. Let's just set them equal to each other. Okay, so we set them equal to each other. I'm going to go through solving this very quickly because we hopefully have this down pretty quickly, but if you want to, you can try and solve it on your own. And mine should load in a second. And it should be loading now. Okay, so I went through and solved this. I added 6x to both sides. I divided both sides by 6. I factored out an x, and then my solutions are 0 and 2. I didn't go and solve those linear equations, but... Okay. So now we have our bounds of integration from 0 to 2. But we still need to figure out which one's bigger, which function is on top. So let's draw a little sketch to give us an idea. Well, I know I'm going to be touching at 0 and 2. And how you draw your sketch doesn't really matter. Like, I already know that this sketch is wrong, but I just want a picture that I can label, basically. And we're going from 0 to 2. All right, so let's figure out which one's bigger. But the reason I also want to draw this picture is we can see they're only intersecting at 0 and 2. So they're never going to cross anywhere else. So whichever one is on top, it's on top the entire time. Whichever one's on bottom, whichever one's smaller, is smaller the entire time. That's sort of my purpose in drawing this picture. And now let's figure that out. Let's check a number in between 0 and 2. So let's take this function right here, y equals 6x squared minus 18x, and I'm going to try plugging in 1 to see where it is. So if we plug in a 1 there, we get y equals 6 times 1 squared minus 18 times 1. I'm not going to go through the whole computation there, but we get y equals negative 12. Because basically 6 minus 18. Okay, so this is where this function is at in this general area. And now let's check our other function. Y equals negative 6x. Again, we're just going to substitute a 1 in. So, oops, I don't want to use that. So we get y equals negative 6 times negative 1. Y equals positive 6. And this will tell us which function is going to be on top. Which number is bigger? Well, this y equals 6 is our bigger number. Let's go ahead and label it on our picture. We have negative 6x is the top. And then we have our 6x squared minus 18x on the bottom. So this picture does not line up with what this graph should look like. And I'm okay with that. I just wanted to see the little area and be able to label it. I don't know why it's not drawing. There we go. Okay. So now let's go through and actually compute this integral. So our bounds are from 0 to 2. So we have the integral from 0 to 2 of our bigger function minus our smaller function. Our bigger is this negative 6x. So we have negative 6x minus, and it's minusing all of our smaller function. Our smaller function is 6x squared minus 18x. So I'm going to put it in parentheses so I don't forget that I'm subtracting the whole thing. And of course, we don't forget our dx on the integral. And now let's just simplify this a little bit. We get 0 to 2, negative 6x minus 6x squared plus 18x dx. And we can clean it up even more. This is the integral from 0 to 2 of negative 6x squared plus 12x dx. And now we'll actually compute the integral. Well, I'm going to add 1 to the exponent and divide by the new exponent. So I'm going to have x cubed, and I'm dividing by that new exponent. I'm dividing by 3. Negative 6 divided by 3 is negative 2. And then we have this positive 12x. I'm going to add 1 to the exponent, so that's going to give me x squared. And I'm going to divide by that new exponent, so we're dividing by 2. 12 divided by 2 is 6, so I have positive 6x squared. And we're integrating from 0 to 2, which this is a very nice integral because hopefully we can clearly see that this 0, that's just going to go away, so all I care about is the 2. But I'll probably write out the whole thing so we can see it. But that's negative 2 times 2 cubed plus 6 times 2 squared minus all of our negative 2 times 0 cubed plus 6 times 0 squared. And I know it's not loading, but it's about to load, and then I'll just see it. So yeah, just substituting in using our first fundamental theorem of calculus. And now this whole thing here, that's just going to go to 0, so I'm not even going to bother with that. And I'm just going to look at this part here. 2 cubed is 8. 8 times negative 2 is negative 16. 2 squared is 4. 4 times 6 is 24, so we have negative 16 plus 24. I think I might have made a mistake. Let me check my work. Oh, okay, I made a mistake on my key, but my actual one is right. Okay. So we get negative 16 plus 24. Of course, that's just 8. So this is our total area between the regions. Okay, so there's that one, and our last example that we're going to do together, this bottom part is going to be for day 2, so I'm going to do it in a separate video. But this was if we were going in terms of x, and I think so far we should be okay, at least with the process, if not like the actual execution. What I mean by that is like, there's nothing too fancy in our steps. But here I am going to switch it up a little bit, and this part I do think is kind of confusing. So we have several bounds here, actually. And I want to sort of draw a picture. That's actually going to be the first thing I do here. Or a little bit of, start our picture. Because it says, what is the area of the region in the first quadrant? So I'm actually going to draw just a little L, because this is my first quadrant. And it actually tells us more about this picture. It tells us that we're bounded on the left by the graph of x equals y squared over 2. So again, I don't super care what that looks like, but actually I don't want to draw the picture yet. I want to wait until I have my bounds first. But a key thing to note here is that our functions are now in terms of x, not in terms of y. So that's going to change our approach a little bit when we get there. But our starting point, we're going to do the same thing. I'm going to set them equal to each other, and I'm going to see where they meet, where they intersect. So we have y squared over 2 equals 3y minus 4. Go ahead and try and work through it. When I come back, I'm going to have it all worked out, and I'll talk us through it, but you won't have to wait for me. Okay. So I worked it out. Y squared over 2 equals 3y minus 4. I multiplied everything by 2 to get rid of this denominator. So we get y squared equals 6y minus 8. I then moved everything to the same side. So I subtracted 6y and I added 8 to get y squared minus 6y plus 8 equals 0. I factored. I just did that mentally. Y minus 4, y minus 2. Our zeros are y equals 2 and 4. So now I'm going to label that on my graph. And I want to be careful because these are y's, not x's. So I'm labeling it on my y-axis. 2, 4. Right there. Okay, and it actually is nice, and it tells us that we're bounded on the left by the graph of this. It doesn't matter how you draw it, as long as your function is always to the left, and then on the right by that other function right there. So that's going to look like that. So I have it all the way on the left, and then this one's always on the right. And actually, let me redraw this actually a little bit bigger, because I want to demonstrate what's happening with our area. Let's set this a little further apart. Okay. There, my picture should be redrawn a little bit bigger. And now our bounds are for y, so we're going to integrate this with respect to y. So if we're looking for the area under the curve, well, now our area under the curve isn't from here to the x-axis, because that would be with respect to x. It's going to be from here to the y-axis. So let's see what that looks like. And we don't know which function is which yet. Well, actually we do. We know that this one is, the left one is y squared over 2, and the right one is 3y minus 4. Because they tell us. They were fortunate enough to tell us. Otherwise we'd have to find it like we did before. But if I'm looking for the area of this 3y minus 4, the area between it and the y-axis is this whole area right here. And then if I'm looking at the y squared over 2, my left one, well, that's only, oh my god, why did it made my markers fatter than I wanted them to be? There we go. Or my highlighters. Okay. And so that's this area here, and all I want is just this yellow area. So my bigger function here in this case is the rightmost function. It's the 3y minus 4. So let's set up our integral now. So we have the integral, and remember we're doing in terms of y, so we're going from 2 to 4. Our big function is the 3y minus 4. And then we're subtracting that from y squared over 2. And we're integrating with respect to y. Okay, now let's actually integrate this. I'm going to go through this integration pretty quickly, but this one is a little more complicated than the last one because we're going to have fractions. And our numbers are also going to be a lot uglier. But let's go ahead and go through it. We're going from 2 to 4. 3y, I'm adding 1, so we're going to get 3y squared divided by 2. And then we have negative 4, that's just going to become minus 4y. And then we have negative y squared over 2, that's going to be negative y squared. I'm dividing by the negative y cubed, excuse me, divided by the new exponent, which is 3, so that's going to end up being 6 from 2 to 4. Okay, and we'll go through it. Now I'll actually do the computation. You can go ahead and pause the video here. I'm not going to show all this. I'll show all the steps for the computation, but I'm not going to make us sit through going through it. Apart from this first line, actually I will write this first line, because I don't think we all fully know our first fundamental theorem of calculus, even though it is fundamental. So I'm substituting in my top bound minus my second bound. Okay, and now you can pause it, and when I come back, I'll have all this filled out, and you can try and do the computation on your own. I'm not going to fully simplify it. I'm just going to combine the like terms pretty much. Okay, I'm back. I have it all filled out now. I just did each term, and now we'll clean it up to make it look nice. 48 minus 16 is 32. 32 plus 8 is 40. Did I do math wrong somewhere? 4 times. Sorry, I'm thinking I made a mistake again, but maybe I didn't. Oh, I did make a mistake. Okay. I was like, this does not look right. This 48, hopefully you're screaming at it and realizing 4 squared is 16. 16 times 3 is 48, but I forgot to divide by 2, which gives us 24. And that makes my answer a lot more reasonable with how I worked it before. Okay, 24 plus 8 is 32. Negative 16 minus 6 is negative 22. 32 minus 22 is 10. I think I made another mistake on computation. Yeah, 32 minus 22 is 10. And then we'll combine our like fractions, which is just negative 28 over 3. Hopefully I didn't make any other computation mistakes in there. I guess y'all will be able to tell me if I made any other mistakes in here, but hopefully I didn't. Okay, and this is the area in the region. Okay, there will be a practice up for this, which I'll give instructions to in Canvas. But this is as much as I want you to be able to do on day 1 of this. So hopefully this helps. Thank you for watching.